Hello, my name is Jonathan Weaver, Professor of Mechanical Engineering at the University of Detroit Mercy, and this will be a brief introduction to the Systematic Innovators Toolbox that I've developed and have been teaching with for most of my 30 years at the university. This particular version is geared toward faculty who teach engineering design and who are looking to create more innovative, entrepreneurially minded engineers. Before we go any further, just my definition of innovation. You can Google it and get countless other definitions. Mine's pretty straightforward. First of all, a lot of people confuse innovation with invention. I make a distinction there. Invention, at least by the U.S. Patent and Trademark Office, per the requirements to actually get a patent, requires three things: novelty, usefulness, and non-obviousness. So I like to say that innovation starts with invention, may or may not involve a patent. It must be commercialized. You must see it through and do something with it. And then you shouldn't regret having done it. So that's kind of what I'm working with. So why is innovation suddenly such a popular term, corporate mantra in many cultures? I would suggest that when I was in school, my professors were teaching me failure mode avoidance. So I was learning how to design bridges that wouldn't collapse in moderate wind, make design changes or understand the loads involved in supporting a walkway at a hotel and make sure things don't collapse and kill people, understand stress concentration so I don't put up square windowed airplanes, pressurize the cabin and wonder why they explode, and get my interfaces right so that O-rings don't leak and cause catastrophic failure of spacecraft. So I learned how to avoid, do the right analyses, design components, and make sure those types of failures didn't happen. And I think I did a pretty good job of learning those techniques. Just a quick reminder, as pointed out in this text here, is that nearly all engineering failures result from faulty judgments, not faulty calculations. So why is it that we are so good at producing the wrong products, products that customers don't necessarily want at the price point that we expect we can make money at, but yet we can do that with Six Sigma production capability? We can make exactly the wrong product over and over and over again. So to answer that question, I want you to reflect and think for a minute. What tools and techniques and methods did you learn in your technical education? And if, like me, you're an engineering professor, you're probably teaching based on what it is that you've learned. A recent workshop that I was involved in, some typical answers from the faculty members who were involved in the workshop looked like this. So pretty much typical things that you would cover in a technical class. So you'd learn heat transfer and fluid mechanics and statistics and Newton's laws and how to design heat exchangers and on and on and on. You can almost take the name of a course, with the exception of maybe capstone design or intro to design, and the course tells you what you're going to learn. You're going to learn finite element methods. You're going to learn dynamics. You're going to learn mechanics of materials, etc. In electrical, maybe you're learning control theory and circuits and whatnot. My background is mechanical engineering. So I would suggest to you that the typical engineering education, in other words, the tools and techniques that were just mentioned when asked what you learned and what you generally teach, equips you to work on only one box in a generic product development process. For simplicity, this is just showing a linear model of the major steps in developing and releasing a mass-produced product. And if you reflect and think about all those techniques I just mentioned, I would suggest that they really only qualify you to work in detailed design. They really don't teach you much about any of those other boxes. So shouldn't you learn and teach some tools and techniques for the other steps in the product development process? By the way, the World Economic Forum top skills for 2025 include things like analytical thinking and innovation, creativity, originality, and initiative, and reasoning, problem solving, and ideation. So a lot of the tools in the toolbox I'm about to reveal to you, try to address those capabilities, skills. I've come up with a little analogy to help you understand where I'm coming from with the toolbox. If I were to run in a marathon, it would be not pretty. I'm almost 60 years old. I have an artificial hip. I have some fused vertebrae in my back. I'm not particularly fond of running long distances, so I probably wouldn't finish. And if I did, it wouldn't be very, very good time at all. I don't think I'd even finish. But yet, if you gave me a tool, in this particular case, a bicycle, I would still beat every marathon out there, even given my handicaps. But with a decent bicycle, I can easily do well under 2 minutes for 26.2 miles, which is a milestone yet to be broken on foot. But that tool is really just leveraging my natural capabilities in a far better way than running, putting one foot in front of the other, repeating that over and over. So there's, assuming I'm not cheating with a modified electric bike or a fuel cell hidden in there somewhere, it's really just leveraging my own capabilities in a far better way than running the marathon. So the toolbox I'm about to reveal to you can be described this way: is I think it's full of bicycles for your brain, tools to make your brain work better. So it turns out I came up with this on my own, but then I later learned that back in 1981, Apple had an ad that talked about computers being bicycles for the mind. So a similar analogy or metaphor, whatever the right word is there. So basically, all these different bicycles aren't the same, just like you might have a road bike and a mountain bike. There are different tools for different applications. And so just like you would a mechanic's tool sets, where you might put a drawer full of pliers, a drawer full of wrenches, a drawer full of hammers, etc., I've come to organize the tools that I typically teach engineers into 3 drawers for kind of convenience sake to understand how they're organized. Those 3 drawers I label strategy and problem definition, kind of the very front end, ideation or concept generation, and idea management and implementation. I started my work primarily in the ideation, the center drawer, concept generation, and that's still where I have the most fun and where most of my tools lie. But I quickly learned that a lot of the mistakes in product creation end up in the first or third drawer, so I quickly had to learn many other tools and respond. So I'm going to quickly introduce these tools. Later in the presentation, I'll take 2 of them and go into just a little bit more depth so you get the sense of it. But each tool can be a separate, depending on the complexity of the tool, short lecture to half a day or a day even, to get a good handle on each tool. Some of them are very, very much shorter. So in the strategy and problem definition drawer, I put things like ethnography, blue ocean strategy, offshore trends of technical system evolution, recently AI, things like ChatGPT, search for the real problem, it's really around problem definition, 9 windows, another trending tool similar to Altshores in that it's a trending tool, painstorming, kind of a play on the word brainstorming with looking for pain or opportunity, and the Kano model of customer satisfaction. So I put those tools kind of in the front end, helping me figure out where the opportunities lie, what I should be working on, what problem statement I write based on that opportunity, what my competitive strategy is, things of that sort. This next slide just presents them in a slightly easier to read format, all in one list. So those are the strategy and problem definition tools. Again, my fun started in ideation. If I think about all the tools for ideation, crazy eights, lateral benchmarking, provocation, trees, brainwriting, the concept fan, heuristic architecting, trimming, functional decomposition, Shindagu, bisociation, biomimicry, concept combination tables, axiomatic design, design heuristics, or blue sky thinking. This is where many, many tools can help you generate more, broader, and generally better concepts. And you'll notice brainstorming isn't even on my list. Go ahead and do it, but at the end of the day, I believe your best ideas will come from having used these tools. It probably won't be one of the first ideas that you wrote down in an open brainstorming session. This is just a cleaner list of those ideation tools for reference. And finally, on the back end, what do we do with all these ideas? How do we implement them? What are some of the roadblocks and processes we can use to take the great idea and get it over the finish line? So analytic hierarchy process, AHP, or Pew matrices tend to be some down select tools. Edward de Bono's 6 hats is more about group dynamics and working, but I lump it into this back drawer for convenience. Metzger's sequence, odd as Ken will. The Will It Fly scorecard, which asks the business question, not just the technical readiness question. Is your idea going to fly? Personas of innovation. Not everybody is cut out to be an innovator. Some want to be implementers, and that's perfectly okay. Just want to make sure people understand the different personas and are working per their own persona. And then a lot of details about implementing innovations. A lot of work by Govinda Rajan on things like the other side of innovation. So there again is just a cleaner list of the tools for drawer number 3, portfolio management. So just a thought here, to get a good idea, you need a lot of ideas. Bob Sutton's done a lot of research in this. He says it takes about 4,000 ideas to get 2 or 3 commercial successes. 4,000 raw ideas, 226 of them will get prototyped to some level. 12 of them might get further incubation and investment. And a couple of those might actually come out and you don't regret having done them. In other words, we'll call them success. I got 2 slides talking about some of the hurdles to systematic innovation. I won't go through the whole list with you for the sake of time, but I want to point out some of the ones that tend to jump out at me with student projects. I do a lot with students at various levels, undergrad and grad, but I also do a lot with practicing engineers, and the list remains the same. But I think if you've taught students design, you'll notice they generally have a lack of good, what I'll call game-changing ideas, jump into a new curve with a non-obvious, non-incremental idea. In my opinion, people have the incorrect sense that brainstorming is sufficient, and having done that, we have 7, 20, 50, all the ideas we need, and one of them must be good. Generally, people are not aware of this set of tools that I just mentioned, so they don't know what they're missing. They're running the marathon not knowing that a bicycle exists. On the next slide, a few more. I think from a student standpoint, you tend to see this last one, tendency to run with the first seemingly potentially feasible solution, especially if the problem seemed hard and the solution wasn't obvious. So just remember this analogy. Riding a bike is to running a marathon, as using the systematic innovation toolbox is to just brainstorming. It's like bicycles for your mind. You'll get more ideas, you'll get better ideas, you get more conceptually diverse ideas. Just along those lines, if the only tool in your toolbox is a hammer, then everything looks like a nail. I think we've all heard that. So I would say if the only tool in your innovation toolbox or your ideation toolbox is brainstorming, then brainstorming will look like the answer to every one of your problems. Just a quick note, you probably didn't learn. I'm assuming most people watching this know how to ride a bike. It's okay if you don't, but for those who do know how to ride a bike, you probably remember a little bit of a learning curve. You might have fallen off a little bit. You might have learned without pedals or possibly with training wheels. You might have skinned your knees or your elbows a few times, etc. So along those lines, once you learn to ride the bike, you'll outperform the marathon runner. And similarly, once you learn the systematic innovation tools, you will massively outperform anyone doing just brainstorming, but you have to learn them. And there's a little bit of a learning curve. It's not just I'm aware that a bicycle exists, therefore I can ride it, nor is it I'm aware that the innovation tools exist, therefore I'm good at using them. So what we're going to do with the limited time we have together here is a quick introduction to 2 of the tools in the systematic innovation toolbox. I'm picking biassociation and biomimicry. Both happen to be in the ideation drawer, just to give you a sample. So let's start with biassociation. First of all, this is a very abbreviated version, just to keep this video manageable in the hopes that more of you will see it to the fruition. But a full version can be found by scanning that QR code if you're interested in what I actually do in workshops or student classrooms. So I started with a hypothetical question. Can you save our hat company? Pretend you work for a hat company and we're struggling. It's a red ocean, for those of you familiar with the blue ocean, red ocean analogy here. It's a red ocean of competitors all having very similar products, very difficult to make money on. And so pretend for a minute that you work for a hat company and your leaders have come to you and said, we need ideas for a new or improved hat. Will you please brainstorm some ideas for a new or improved hat? So here's an exercise. if you have the time, I think you'll find benefit in pausing the video here and actually trying this along with the follow-on exercise in a few minutes here. But time yourself, allow yourself 3 minutes, and just write down as many ideas as you can for a new or improved hat that will keep your hat company in business, save your job. Focus on the hat itself, not marketing or supply chains or anything of that sort. Just at the end of the day, customer wants a better hat. So try to think of better hats. So again, if you have time, go ahead and pause the video, write down your list, and we'll come back to it later. And hopefully you'll feel what it's like to use one of these innovation tools in a few minutes. All right, so if you've done that, count how many ideas you've had and just circle. You know, you had 5, 7, 10, 20, whatever your number was, however many ideas you had. So let's return to what is bisociation. I believe the term was coined by Arthur Koestler in his book, Active Creation, where it's the creative process consisting of discovery of hidden similarities. Basically, it involves connecting two seemingly unrelated or random things, forcing an association where it's not obvious. Engineers are generally pretty good at associative design. You know, if you design cars, you're going to look at anything with wheels, you know, trucks, tractors, anything that moves people, airplanes, etc. Those are not unrelated. Those are related stimuli where I hope you're doing that just out of good associative thinking. The point here is that oftentimes a seemingly unrelated stimulus can give you a good idea. Anybody familiar with Tom Kelly's work? Tom Kelly of IDEO, his book, 10 Faces of Innovation, has a chapter on the cross-pollinator. Cross-pollinator is the person who can routinely do bisociation. And I find it to be an effective, very easy tool, very easy to learn to ride. It's like the tricycle. Even before you worry about falling off the bike, learn to ride the tricycle. So it's a very easy tool to introduce, a good place to start. So bisociation, in a nutshell, uses a random stimulus to jumpstart your thinking. Basically, the way your mind organizes your thoughts or your knowledge is similar to what you would do on a computer. You put things into almost like folders, areas. You know, here are my work ones, here are my fun photos, here are my sports, here's my finances, whatever. And generally, the way you then solve problems is you only look in the obvious drawer. If I were looking for a work folder file, I probably wouldn't look in my vacation folder. But yet the inspiration to a better work result might lie in something you did on vacation. So the idea is that your mind, when you're not busy, actually takes intersections of seemingly unrelated stimuli and searches along there where there might actually be a good idea. So a lot of people report they, were walking down the beach, about to get in the shower, almost asleep, whatever, and they suddenly had the inspiration. And what the research appears to show is that was that random connection your brain made when you weren't even thinking about it. And so it begs the question, if those types of connections might eventually help you solve the problem, why wait for that random connection to happen when you're almost asleep or in the shower or whatever? Why can't you force it? And it turns out you can, and it seems to work very well. I, of course, was skeptical, like you probably are, that this could ever work. But I've been proven wrong so many times, it's now one of the most effective tools in the toolbox. So we'll play a simple game. You can play it with the students if you're doing this in the classroom. But A plus B equals C. In this case, A and B will be two things that seem unrelated, and C is the new idea. When we're doing this on a real project, I'll say A is the problem I have at hand, B is some random stimulus, and it generates a new idea. You can certainly do this with just purely random stimuli and get a product, but it probably won't help you solve the problem at hand. So when we do this for real, A would be the problem at hand, B would be some random stimulus, C would be a new idea. But just to give you an idea how other people have done this, A would be an auction, B would be symbolic of the internet. And of course, if you combine an auction with internet, as Pierre Omidyar did, you create a lot of value in a company called eBay, and particularly, I guess, PayPal to manage the money, but it all comes down to the idea of the auction in the first place. So that would be this idea of seemingly random connections. Next one would be A. I believe that's a rubber plant, a picture I took in Florida one time where the label on the tree trunk said it was a rubber tree, so I presume that's correct. B would be a waffle iron, of course. And some of you may know the story where a waffle iron. It's by Bill Bowerman to create the soul of Nike athletic shoes, trying to design shoes as synthetic tracks and athletic field for coming to play, and conventional cleats were tearing up the synthetic fields. So something to give you decent traction um, on those fields without destroying the field itself or the track itself. Incidentally, that happens to be a picture of the Bill Bowerman prototype waffle iron that he used to create his first sole by literally pouring rubber into the waffle iron. Another one that a lot of you may be familiar with comes from the idea of a bookmark, marking the pages of music at church, and the glue that doesn't really hold quite the way you would expect. Some of you may know the story, but it was a 3M engineer who combined this idea and ultimately created the Post-it note. So it's a great story of making a connection, in this case to a failed glue experiment, back to, hey, this would be great if I could just temporarily stick this in a book or on a computer screen or at somebody's desk. So another one would be a playground, A mechanical water pump, B. Combine the two, and you might get a kid's merry-go-round or playground where the water pump is actuated by the kids playing rather than monotonous handle up, handle down chore, right? So take fun and turn it into pumping the water necessary for agriculture and sustaining life or whatever in the village. Next one's kind of fun. A is a flower vase. B is a fire extinguisher. So A plus B, Samsung created the flower vase. It's a throwable fire extinguisher. It's filled with a fire suppressant made to shatter if you throw it at, say, the stove or corner of the house that's on fire or something of that sort. So in the full version, there's a video that explains it better than I just did. You can watch that if you're interested. Next would be a bird cage. A lot of open space inside, kind of vertical columns, right? But most of the interior is highly usable, and yet it's structurally sound. B would be a heavy book. And if you combine those, if my memory is right, it would be William LeBaron Jenney, architect in Chicago, designed the first exterior steel-framed architecture skyscraper, or at least multi-story building. The home insurance building in Chicago was the original building. Now, of course, we've learned about triangulation and stress. We don't build rectangles that tend to fold or collapse, turn into parallelograms. So that would be the John Hancock building now in Chicago, which uses triangulated exterior steel frame. As long as we're talking about skyscrapers, some of you may have heard the story, but the architects of what used to be the Sears Tower, now the Willis Tower in Chicago, were inspired reportedly by one of them dropped a pack of cigarettes. The cigarettes slid out to various lengths, kind of like shown in the picture there. And that inspired the idea of the various towers at various heights of the Sears Tower / Willis Tower now. So there's many, many more examples like this in the full version that I referred you to earlier if you're interested. The students love playing the game A plus B, who can figure out C. And it's a really powerful reminder that this is not just a random, weird, rare thing that happens. It actually happens all the time. So let's return back to your exercise. If you think about what you know about insects, I assume we're all aware of insects. Most of us probably know they have 3 body parts: head, thorax, abdomen, 6 legs, antennae. Some fly, some bite, some are beautiful, some pinch, some eat other insects, some create light. Many of them morph through different larval to adult stages, etc. So think about insects for a minute, whatever you know and whatever your experience is with them. And then we're going to try this with the A plus B equals C idea, where A is going to be that hat problem I gave you earlier. But now instead of just asking you to randomly brainstorm or just outright brainstorm, I'm going to ask you to think about insects for about 3 minutes and generate new ideas. So again, if you're doing this, if you have the time and luxury to be able to pause it back at exercise 1 and do it, then go ahead and do exercise 2 as well. Pause the video, take 3 minutes. A couple things on this slide aren't relevant because we're not using the Google Sheet to track results. But other than that, I forgot to edit that out. I won't take the time to change it right now. But take 3 minutes, pause the video, and think about new ideas for hats based on your thoughts about insects first. All right, so I've had a little pause there in case you actually paused, so I'll get back into it. By the way, people tend to get some pretty interesting ideas. So, for example, when I do this, I think uh, all insects have antennae, and I think I live in the United States where cell phone service is questionable. I can't even get out of my neighborhood sometimes without dropping a call. And it'd be nice if I had a better antenna. And my hat is much bigger than my cell phone. So perhaps my hat could double as a larger antenna and send a Bluetooth signal down to my phone with the data or the signal. Another idea I've had is when I think about bugs crawling up the wall, I see that in the house occasionally, more often spiders, but even just regular insects crawling up the wall. Wouldn't it be great if I could take my hat off, throw it on the ground, have it crawl up the wall like a bug and hang itself up on the hook on the wall on the hat rack? So that's just a sample of that. So if you did the exercise, if you took that time to do that, I think you'll probably have had new ideas you didn't have when I asked you to brainstorm. And if you think about it, I don't think I would have had ideas like better antenna or hat climbing up the wall like a bug and hanging itself up, no matter how long I had just brainstormed in the original exercise. So think about if you had 2 hours to brainstorm as a team of, say, 5 or 10 on a real project, how many ideas do you think you would get? Do you think after 2 hours you're still generating new, high quality, conceptually different ideas, or you're just generating more and more sort of incremental, similar ideas, or maybe none at all by the end of 2 hours? So rather than brainstorm for 2 hours, think if your team had broken up, each taken 3 to 5 minute little sub periods, each taken different random stimuli for that 2 hour period, and use those to jumpstart your thinking and generate a wide array of conceptually diverse, sometimes typically better ideas, or at least some of the ideas will be better. And by the way, not all ideas have to be great. You only need one great idea in the list. It's okay if the rest aren't particularly interesting or good or useful. But think about that, and you should feel your thinking change. So this is an example where you can feel the tool change your mindset, the way you actually ideate. It's a nice chance to point out for students who think they take a lot of courses and learn about a lot of things that aren't relevant because they just want to do engineering, that those irrelevant things put a lot of knowledge in your brain. So do your day-to-day experiences and your travel, and just everything that enters your memory can be drawn upon in this. So for example, if you didn't know what an insect was because you were caught up in doing nothing but analysis for your whole life, and I asked you to ideate around insects, it probably wouldn't help you a whole lot because you don't know anything about it. So the bisociation process is actually super simple. Any random stimulus will work as long as you know something about it. It's not bad to have something you can use multiple senses. So put something on the table, pick it up, and feel it, bounce it, whatever. You can use really any random nouns. Nouns generally work the best. But temporarily forget about the problem at hand and just think, what do you know about the stimulus? So insects, wings, legs, body parts, exoskeleton, on and on and on, right? And then bring it back to apply it to your particular problem. All right, so that's a very quick introduction to bisociation, one of the simplest tools in the toolbox. Surprisingly effective, especially given how simple it is in my experience. So let's move on to biomimicry, also known as design inspired by nature. Again, this is a very abbreviated version. A full-length version can be found by scanning this QR code. If you're interested in many, many more examples and a lot more depth, you can find it there. Just for context here, if you were to map the entire history of the Earth, roughly 4.5 billion years, onto a 24-hour day, you'd find that humans really only came into existence during the last minute and 17 seconds. So we haven't been around very long. Origin of life is approximately 4 billion years, 3.88, maybe further. But the point is, other life has been around much, much longer than that last split second that we've been around as a species. So perhaps we can learn something from all the amazing evolutionary experiments that nature has conducted that lead to some incredible mapping of function to form. So that's the basic idea of it. It's not a new idea. It's been around for a long time. Ancient Chinese created kites mimicking birds and the way leaves flutter and fall. Leonardo da Vinci, amongst other things, practiced biomimicry, studying flying and other types of natural structures, wing structures. Back in 1799, inspiration from electric eels led to the development of batteries. There may be evidence of much earlier simple chemical batteries, but certainly studying the eel led to some new insights. 1818, Mark Isambard Brunel, father of Isambard Kingdom Brunel, patented a tunneling shield inspired by the way shipworms are able to burrow through the ground. GE researchers looking at how earthworms and roots are able to tunnel. So lots of stuff. Lots of advantages for doing this. I won't go through the whole list here in the sake of time. But just in a nutshell, the purpose of each of the tools here is to generate more, better, broader, conceptually different ideas than you got through just brainstorming. So this is one way to do that. It's a way to help you make connections to natural inspiration that will lead you to ideas that you probably wouldn't have had otherwise, and they may be better than the ideas you had previously. Biomimicry can be practiced via either a push model or a pull model. We'll cover both, but an engineer would typically want to use the pull model. In the push model, you start with the technology, the form, the biology, and then you look for an application. In the pull model, you have a certain function you need to deliver. You have an engineering problem that can be satisfied by delivering such and such a function. Then you look for the biological inspiration. What in nature provides that function, and how can I learn from that to design my solution? We'll take a quick look at the push model just for completeness, but it's the pull model again that will be relevant to engineers. You may be familiar with the story of Velcro, where a Swiss engineer studied the cockleburr sticking to his dog and went on to create Velcro from that inspiration and got patents and did quite well with it. Somebody studying rat's teeth noticed that they can gnaw through drywall, wire, wood, metal, and their teeth never get dull. And it has to do with the layering of a sharp or harder material on a softer material. And so they were able to create cutting devices, things like saw blades and milling blades that self-sharpen rather than becoming dull. So there's lots more examples of those where biologists have learned something interesting and eventually were able to push it out and create a product with some help, usually from engineers at that point. But as an engineer, we don't usually have the luxury of just studying the biology in the hopes that someday we'll have a great inspiration. So normally as an engineer, we're going to go with the pull model. Recall that the pull model here, we need to deliver a function. We're going to look for the inspiration. So one such example would be Joseph Glidden, as the U.S. pushed westward, trying to develop a way to stop animals from leaving your property or your range. Realized that the hawthorn bush did that and basically was able to create barbed wire by mimicking, finding a way to mass produce something that mimicked the effect of the hawthorn bush. Another common, well-publicized example stems around the Japanese Shinkansen or bullet train. Problem they were having was you'd go through a tunnel, and the tunnels were designed with minimal clearance when the trains didn't move very fast. As you start going faster and faster, the train almost becomes a plunger, pushing air through that tunnel as it goes. And then suddenly you have an open cross-section at the exit of the tunnel, and you get a big expansion of that pressurized wave of air in front of the train. And you get a shock wave. It's not exactly a sonic boom, but it's similar in effect where it can break windows, hurt your eardrums, etc. So turns out, if you think about that problem, it's the train going from pushing pressurized air to suddenly it's at 1 atmospheric pressure at the exit of the tunnel. And it turns out the surface of the Earth is covered by a boundary layer between different density fluids. Approximately 3/4 of the surface of the Earth is covered with such a boundary layer between air and water. And so the engineers turned to the kingfisher, and it's able to dive across that boundary layer without shock waves, without a lot of turbulence, without a lot of loss of energy. And so the story goes that they literally sectioned the beak and modified the front end of the train to be basically a scaled up version of that geometry. This was long before, this was in the 60s, if I remember correctly, long before computational fluid dynamics would allow you to come up with that shape and understand why why that eliminates the tunnel shockwave problem. So it was highly successful. In fact, it was so successful that they also had a wind noise problem on the pantographs, top of the train where it takes off power from the high voltage catenary wire. And it turns out if you study the owl, you can learn how it flies very silently, so prey doesn't see it. Turns out that it has to do with the fact that that trailing edge of the wing is both nonlinear, which separates the phase in time, and different shape and radii feathers, which separates the frequencies. So you're mixing the turbulence off the back end of the wing in both time or phase and frequency, so you don't hear it. So it turns out they were able to do something similar to the shape of the catenary, and now it's done on automotive mirrors and roof racks and antennae and things like that to make them quiet as well in the wind. And you'll even see it on some Boeing. That's a Boeing 787 Dreamliner. It has, obviously Boeing didn't make the engine. I don't recall who made that particular engine, but point is some of the modern jet engines are doing something similar to try to deal with the noise. There's a link here. I'm not going to play it in my recording, but you can learn about how slime mold helped Tokyo understand which routes would be basically most popular, most efficient to lay the subway line by modeling slime mold. So I'm not a slime mold expert. I just found it interesting, that particular video, if you want to watch it. Termite mounds are very interesting. They stay roughly the same temperature day and night, even though temperature outside might vary from 3 degrees Celsius at night to 42 degrees Celsius by day. So there's a number of buildings. Eastgate Center in Zimbabwe is shown on the left there. A number of other buildings that have been inspired by understanding how termite mounds use natural circulation, natural heat sinks to be much more efficient. If I recall correctly, the Eastgate Center uses about 10% of the energy, not saves 10%, uses only 10% of the energy of a typical building of its capacity in terms of utilization space. Another one is sharks. Some things have been done in swimsuits, but this particular example is more about the antimicrobial features that keep algae and things from growing on the shark. And surfaces inspired by that microstructure are now in things like hospitals on push buttons and door panels, and light switches are things where you might not want germs to transfer near a neonatal ICU unit, for example. Another kind of fun one is the way the Namib, if I'm saying that correctly, desert beetle collects water by its body, cools off at night, comes out in the morning, and moist air, warmer moist air comes over, cools when it hits its body, condenses, runs down, it gets a drink. So a lot of people are making sort of natural moisture or humidity harvesting devices that work in a similar fashion. There's a link here if you want to watch it about, it's actually a link just to the audio version of it, but it's interesting that bats can fly out of a cave in large quantities, flying in XYZ roll pitch yaw, not even just a linear path. And they don't crash into each other, and they're using echolocation, where everything we know about echolocation or signals like that is that they should be self-interfering and unable to actually diagnose anything from all those signals happening simultaneously. But somehow they figure it out. So I think we're making a lot of mistakes with our approach to self-driving, but one of them, one suggestion is maybe go study the way locusts and bats are able to navigate in swarms. So there's a biomimicry Pinterest board started by my colleague, Dr. Klinke, but I pin to it very, very often. It's now over 1,600 articles, much more than when that picture was taken there. You'll find articles on almost everything imaginable, from structures to electronics to fashion to robots to, like I said, you name it, it's up there. So a great assignment for students is to go through there, find something they're interested in, do a little bit of research, write a quick summary of it, talk about how it maps function to form. So that begs the question, if I know what function I do need to deliver, and by the way, functional analysis is a whole other tool in the toolbox. You need to be able to describe in a solution neutral way what you're actually trying to do. It seems, imperative to me that that be another skill set that we teach engineers to do a better job of. But anyway, now what do I do? What if I have no idea how nature delivers that particular function? What do I do? And these are some possible ways to do that. I particularly like the third bullet here, asknature.org. They have a functional taxonomy. It's in the language of biologists, not language that most engineers would use, but right now it's a free, widely available resource that works quite well. I've had pretty good success both with student projects and real industrial applications. A whole other story is biotrees, blending this with theory of inventive problem solving. That's beyond the scope of this little piece of the lecture. So here's a quick example. Suppose you have a problem with a long, slender part failing due to buckling. Maybe it's an A, B, C, D pillar of a car when it rolls over and the roof crushes, or the sill in the car that foreshortens when you're in a head-on collision and you lose what is normally your seating space. So if you were to look at asknature.org, and the website changes, so it may or may not look exactly like this now, but if you navigate it, you can figure it out. Biological strategies would be where you wanted to go. And eventually you'll get a list on the left side that looks like this. You'll see things like break down, get, store, distribute resources, maintain community, etc. If you expand, protect from physical harm, you'll see prevent structural failure. So buckling would fall under that subcategory in the taxonomy. And if you do expand the prevent structural failure, you'll see prevent buckling, prevent deformation, prevent fracture rupture. So obviously we're looking at prevent buckling. And the little number 21 next to it tells you that at the time I took that screenshot, there may be more now, I'm not sure. But anyway, at that time there were 21 articles about how nature, most of them are about nature. Occasionally you'll see a company or a product that illustrates it, but most of the articles will be straight from nature. So you can see a whole bunch of different things there. So you go explore those 21 different things. So for example, you might look at how thin-walled tubular stems of long, tall plants don't buckle. You might look at how porcupine quills don't buckle. You might look at how bamboo doesn't buckle, right? This would be the porcupine quills. So there's some great links in there, some articles you can read directly. It can point you to authors who generally are going to be happy to help you if you have an engineering application related to their biological research. But you can go do just some digging and learn what you need to know about, is it the material, is it the geometry, is it the microstructure, is it something the way it's controlling the loading, what is it that makes these things in nature seemingly defy the buckling problem. Just a quick note, most engineering complex problems that are complicated or non-trivial will involve multiple functions. So there's a pretty interesting front-end biomol that can help you search multiple functions simultaneously. There is a ton of work, more of it's covered in the expanded version that we don't have time to go into here, of other people trying to create this roadmap of how I can get the right inspiration to my particular engineering problem. One of them is NASA's periodic table of life. It's basically going to go out and using kind of a large language model, AI type algorithm, try to read all of the valid, peer-reviewed biological literature and try to distill that into a useful alternative to you having to do the functional taxonomy to help you find the right inspiration. By the way, if you take the fan-out version of the Ask Nature taxonomy, it looks like this. So the top level in dark blue there, everything from move and stay put to get, store, and distribute resources. And then under each of those is a subgroup, and then finally the sub-function. By the way, when I first started learning about biomimicry, I couldn't really find too many companies that said they practice it routinely. Occasionally you'd get a lucky one-off engineer who had a hit. But nowadays there's quite a few companies that are practicing it strategically or regularly or whatever the right word is, not just one engineer happened to get lucky doing this. So quite a few companies are noticing that this can really help you. So bottom line is, let nature inspire your next innovation. And if you've survived to the end of this 45 minutes, I hope you're interested in learning more. Workshops are available. They can be designed for faculty members who might teach students design methodologies and tools. Can be designed for students just to get them aware of some of this, and can also be designed for practicing engineers in industry that will change the way they do product development forever. So if you're interested, there's my contact information. Let me know. Thank you very much, and happy innovating.